This conference will now be recorded.
Before we begin, the meeting is being recorded and will be posted on YouTube afterwards. Everyone who speaks during today's event will be part of the recording. We will do the Q&A at the end of the presentation. If you choose to ask a question, your voice and image, if you have your camera on while speaking, will be part of the recording. If you do not ask a question, you won't be part of the recording. If you're using the most recent version of the app, which we recommend, you can use the raise hand function to join the queue. If you're using an older version of the app, which does not have this function, please use the chat to let the organizers know you would like to ask a question, and they'll add you to the queue. The organizer will let you know when you're next in the queue so that you can be ready to unmute your microphone and ask your question. If you do not want to be part of the recording, the organizers can convey your question to the speaker. In that case, please type out your question in full and let the organizers know you would like them to present it to the speaker. If you have any technical issues, please message the organizers for assistance. If you drop out of the meeting and are unable to rejoin, you can post a message on the event page on Meetup, which we're monitoring during the presentation. SFPUG Bay Area Postgres is a PGUS affiliated user group, and I'm a volunteer for PGUS. SFPUG is sponsored by PGX, and I work for PGX. And if I could have everybody except the speaker mute your microphone and go ahead and turn off your cameras. It looks like everyone's got their cameras off. James, I'm going to go ahead and make you the presenter. There you go. And without further ado, here is James Arthur with syncing Postgres into the client.
Thanks very much, Catherine. Nice to meet you all. There is something a little magical about sync, where you just write changes to the database and they are instantly just there. It's like faster than your eyes can move. So, for example, here I've got a PSQL session. I'm just going to insert an item into the database. And as soon as I insert it, it's just there. So bottom left is a sync client that's just logging the events. On the right-hand side, we have a web app using React. And whatever I do to insert, update, or delete, the changes just sync instantly. And whatever I do, it all just stays in sync. And so this runs off Postgres logical replication. And as I imagine we probably all know, Postgres has had logical replication for syncing data for quite a while. I think it's since version 10. Before that, it was PG Logical in version 9, which was released back in 2014. And so if you compare that kind of time frame with the evolution of state transfer technologies, so how you build software applications and how you transfer the data from the back end to the front end, it is pretty much in that period from when logical replication was released that there's been this shift from ad hoc imperative data fetching towards more declarative architectures built on sync. And as we've gone on that journey, the experience of using software has been completely transformed. You've gone from those very clunky old systems like Jira, where you submit the form, you watch a loading spinner, you go make a cup of tea, to really high quality, fast, modern apps like Figma and Linear. And these are two applications that have been extremely successful. I think it's fair to say they both dominated their software categories, design software, project management software, and they've done so precisely because of the quality of the user experience that they've been able to build on sync. So for Figma, it's about collaboration, it's a multi-user system, you have to keep the local data and the changes in sync in real time. Otherwise, people are working on stale data. And for Linear, they use sync to craft a very fast, modern experience. Everything just feels instant. And the key thing with that is that you have to get the network off the interaction path. Because if you have the network on the interaction path, you just can't ultimately make apps that are reliably fast. And so how does that actually work? Like, why aren't all apps built like Linear and Figma, using sync as their state transfer technology? And the answer, obviously, is that it just hasn't been that easy. So let's say we have a Postgres database and we're consuming a change feed into some kind of server, and then we're fanning out that data to clients. And the aim is to keep subsets of the data in the database in sync inside the client. And so if we start with the first part, let's imagine we consume a logical replication publication, presumably through some kind of message processing pipeline. How do you get the right data in the publication? And what happens when the connection drops? Like, it's probably good internet on the back end between the server and the database, but still you have network challenges. Or what happens when you deploy your application or migrate your database, whether that's like schema changes, DDL schema changes, or like database version migrations? And what happens, for example, if there's a bug in the server code and say it stops consuming the publication? So you have all these writes going into Postgres, and it just backs up the WAL, and either the database runs out of storage or the data gets dropped. And so, in a way, this part is kind of the easy bit, but it is already getting a bit complex. And then if you look at the second part, which is filtering and fanning out data to clients, well, how does that work? So how do you do the routing for the data? Are you maybe maintaining some kind of secondary index to look up things like user roles or memberships to do routing and permissions? Or are you querying back to the database to get that kind of information? But of course, with Postgres, you can't query the data at the same snapshot as the transaction that you're dealing with through logical replication, because that snapshot is only available internally inside the database. Once the transaction's been emitted, it's no longer available to query. And if you're running, say, rule logic inside the database on write, you've added a whole bunch of load in a centralized point that's hard to scale. And so there's a whole bunch of these kind of considerations. The real key thing to highlight is the difference between broadcast and sync. So when we're talking about keeping data inside the client in sync with the database, you can't miss a message. So it's not fire and forget. The challenge is you're doing exactly once message delivery across the public internet. And so say you're buffering the messages in the server to tolerate patchy connectivity. Well, we saw before that the WAL fills up if you have a bug in the backend consuming the logical replication publication. But if you're doing buffering in the server, well, now your backend is filling up when you have bugs or failures in the client. And so just sort of stepping back, there are some serious engineering trade-offs in making this kind of system work and scale, between, say, exploding resource use on one side, whether it's storage, memory, or compute, and latency or inconsistency on the other. But we haven't even got to the hard part yet, which is how do you handle local writes? Eventual consistency, conflict resolution, rollbacks, preservation of user intent. And so and they are similar and in different ways. And so, for example, here on the left, Sequin and Feldera, these are kind of in a way like more pure streaming systems. They build arbitrary views. They do incremental computation. So, for example, Sequin here is about high performance change capture and processing. And Feldera here, in a way, it sort of targets real-time analytics, incremental computation. And it's based on a protocol called DBSP, which is similar to differential data flow. It's about sort of efficient incremental view maintenance. And these things are often used to wire up sort of distributed kind of nodes or kind of edge systems. Whereas here on the right-hand side, you have kind of more sort of end-to-end development stacks that are focused on greenfield application development. So these work on top of Postgres, but it's not necessarily Postgres in the sense that they just use it for storage of their data model. So, for example, this is like Instant. It's their DSL for defining your data schema. But this actually then gets turned into tuple storage that's just persisted in a big table in Postgres. So it's not like a sort of data model that you'd recognize that you would design for your own application. Whereas these three in the middle are sync engines that work with kind of real Postgres data models. So Zero is a very cool query through system where you can express relational queries in your application code like this. And then the system essentially takes care of querying through to Postgres, caching, and keeping the results live for you. And ultimately, it's a declarative system, which means that concerns like data transfer and placement can be handled and optimized for you by the system. And in a way, it's like a sync engine is doing for data what a durable execution platform would be doing for compute. And then PowerSync is a more layered system that syncs into a local database like SQLite, and then your application code, you code against that local database. But the one that I want to talk about in more depth is Electric, which is the platform that I've been working on. So Electric is a Postgres sync engine. It's built in Elixir, and it basically takes data out of Postgres, filters it, and then fans it out into local apps and services. So it takes on the challenge of both scalable data delivery, but also partial replication. And it has this partial replication called shape, which is like a kind of subset of the data in your kind of main database model on the server that you would then select to sync into the client. And Electric is designed to work with any Postgres since version 14, and it works with any data model, so including existing data models. There's no limitations on anything like data types or constraints or data model features, and it works with any web stack that speaks HTTP and JSON. So it's specifically designed to sync data through and with existing libraries and frameworks. And so the simplest example of that is React. So this is the code powering that demo that we saw at the start. You bind data to your components, in this case using a useShape hook, and then that data is a state variable that's just automatically kept up to date with the data in your database. But the library that I want to dive into in a bit more depth to give you a real sense of what it looks like to actually build applications on sync on top of Postgres is one that we have recently added to Tanstack. So Tanstack is a popular set of TypeScript libraries for building front-end apps. It actually grew out of a project called React Query, which is now Tanstack Query. It gives you managed queries, caching, mutation primitives, etc. And if we look at how front-end developers use it to build applications, this is idiomatic Tanstack query code. It loads data into a React state variable using a managed query function. And so the function defines how you fetch the data, and then Tanstack query manages calling that function, retrying it, etc. And then when it comes to write, you create a mutator using this use mutation hook with a mutation function that defines how you actually handle the writes, in this case by posting it to your API. And you then use this mutator in your components to make local optimistic writes. And so this code here is how a lot of these type of fast modern apps are being built, because it takes the network off the interaction path. And so how do we plug, say, sync out of Postgres into something like Tanstack? What does that look like? Well, the first thing we need to do is change from fetching the data using that managed query primitive via an API endpoint to syncing the data out of Postgres into the local app. And that means we need a primitive to sync into, which is here shown as the collection. And then we need the local mutations to apply optimistic state to this collection primitive. And then we need to handle the writes by syncing them in the background and then tie the optimistic state lifecycle in with the read path sync machinery. And then we need to be able to bind data to components by querying these collections. And in particular, you're going to want to query across collections so that you can join data up and, in a sense, build views on the sync data in the client, which means you basically need live queries which can work across collections. And so just to recap, you need a collection primitive that works with sync. You need live queries across collections. And you need a way of handling local optimistic writes that not only works with the write path sync, but also monitors the read path sync in order to optimistically discard local optimistic state. And so if you have this, you have a fully working sync stack built directly on Postgres that integrates into Tanstack. And that's called Tanstack DB. So this is a library that was recently added to Tanstack that extends Tanstack Query with collections, live queries, and transactional mutators with robust management of optimistic state that works natively with the sync machinery. And so basically you start using it by defining a collection. So in this case, we're defining a query collection, and this loads the data using a managed query function, which is code we've seen before, right? So the change to your application to use this, if you're coming from something like React Query, is minimal. And then when you have data in the collections, you can bind it to your components using live queries. And to write data locally, rather than the use mutation hook that we saw before, you use optimistic mutation with a mutation function that handles sending the write to the backend. In this case, it posts it to your API, and then calls refetch on the collection. And then to use this mutator in your component, you just call mutate, that starts a transaction, and all the writes within it are instantly applied locally, and then the background sync and the optimistic state lifecycle and any necessary transactional rollbacks are all just handled for you. And so that's the migration pathway from React Query to Tanstack DB. But of course, the payoff with Tanstack DB is the ability to integrate sync. And so the way you do that is, instead of defining a query collection like we saw before, you define a sync collection using Electric, like this. And so this keeps the contents of the collection in sync with the contents of the Postgres database. So in this case, the users table. And it does this using the shape primitive that we have to define partial replication, where you can define whatever filters you like. So a shape is like a filtered view on a database table. And you can create as many views as you like with different subsets of the source data that you sync into your local application. And then to query the data, the component is just exactly the same as before. So the components don't need to know where the data came from. They just work against the local collections. And actually, you can query across as many collections as you like, and they can be collections of different types. So you can sync some data from the database, you could fetch some from an API, you can have a local collection for UE state, and then you can query across them all as part of the same logical data model. And you can have as many complex queries as you like with joins and aggregates, etc., because the query engine is based on a TypeScript implementation of differential data flow. And so when the data changes, it incrementally updates just the relevant part of the result set. And as a result, these live queries, no matter how complex they get, are literally sub-millisecond. And so what this means is when you build out a front-end application on this pattern, you can have lots of components all just running multiple complex live queries. And when the data changes, everything stays well within a single animation frame. So it just feels super snappy and there's no kind of jitter. So just to kind of show this in action, I'll skip the details a bit, but basically there's 3 complex queries here. They're all running multiple joins across multiple tables with thousands of rows using grouping and aggregates, etc. And then the basic JS is basically just sort of hacking the kind of joins in JavaScript. SQLite, you're kind of rerunning the query to get the result set. And as you can see here in Tanstack DB, everything is just sub-millisecond no matter what you throw at it. And then for writes as well, the component code is just untouched from what we saw before with the query collection. And if you want, you can handle writes in exactly the same way by just posting them to individual API endpoints. But also, if you choose to, you can also incrementally move to write path sync with a generic mutation function. And so what we're doing here is whenever there is a local transaction applying changes to any collection, it posts all the mutations to the backend to a generic ingest endpoint. And if it errors for any reason, the local transaction is rolled back. And if it succeeds, the server returns the Postgres transaction ID that the changes were written into the database under, and we then monitor the replication stream for that transaction to come back through to the client before discarding the optimistic state. And so this mechanism for handling optimistic local writes that you then sync in the background is both quite simple and pragmatic in the sense it's server authoritative, you have explicit rollbacks, but it's also relatively sophisticated because you can rebase the local optimistic state on any concurrent changes coming from other users because you're matching on the transaction ID rather than something like the row ID. And then on the server side, you can just ingest the changes, right? Write them to Postgres. And so one reference implementation, just to illustrate, we have is a library called Phoenix Sync. So Phoenix is the web framework for the Elixir programming language. It's kind of the new Rails. And Phoenix Sync is an official sync library that works with Tanstack DB out of the box. And it does a whole bunch of stuff, including allowing you to sync shapes through your backend router, use your controllers as proxies, construct dynamic shapes. And because it's all synced over HTTP, you can just use existing auth middleware or logic to authorize both read and write path sync. So importantly with this model, if you're coming from an API-based application, you don't need to codify your existing auth logic into some kind of database rule system like RLS. Instead, you can just use your existing backend auth logic or middleware to authorize the sync requests. And then with writes, you just ingest them using a normal web controller and then write them to the database. And this Phoenix Sync library provides some utilities. For example, this writer.transactionID function, which returns the Postgres transaction ID that then allows the front end to monitor the replication stream for it. And so that's a kind of relatively low level, just do what you like to write the changes into the database function. The library also provides a declarative ingest pipeline that again allows you to just reuse your existing backend logic to authorize and validate writes. So a bit like on the front end, allowing you to adopt sync with minimal code changes. This is the kind of thing that on the back end allows applications to adopt write path sync with minimal code changes. And if you're not an Elixir or Phoenix developer, this kind of syntax may look a bit weird with pipes, etc. But the same patterns just apply in any web framework. There's no framework-specific stuff here. It's all ultimately just writing the data to Postgres. And so this is the kind of thing that we've been working on Electric, is building these primitives that integrate sync into mainstream development frameworks with an incremental adoption pathway so that you can move towards adopting sync, just one fetch, one route, one ingest at a time. And importantly, so you can do that with your sync stack of choice. So it could be Phoenix Sync with Tanstack DB, it could be Zero, it could be PowerSync with Tinybase or Legend State, and all of these stacks can just run on top of Postgres. And if you're interested in exploring these ideas more, there's a Sync Conf in San Francisco this November. It's on the 12th of November. Both call for papers and tickets are open now. It's a conference for anyone who's interested in or already building on Sync. Which in San Francisco in particular means a lot of startup founders, people building AI apps, agentic. And when you scratch the surface on this sort of next generation of AI apps and agentic systems, you get this sort of whole list of requirements that all steer you into sync. So, for example, resilient token streaming, resumability, interruptibility. Like if we just look at a simple example, this is ChatGPT. It streams the tokens directly from the model to the front end. Any kind of glitch, in this case, like turning the network off, and it just breaks and you refresh the page and it's kind of gone. Whereas if you stream from a model into Postgres and then sync from there into the front end, well, as we've seen, we have resilient message delivery. So for example, here is the same thing built on sync. In this case, the tokens are streamed from OpenAI in the cloud into Postgres and then sync into the front end. And this allows it to just tolerate patchy connectivity, glitches, page refreshes, etc., without a problem. And so, you need other concerns like interruptibility and multi-tab and multi-device. And so as I was saying, like this sort of basic engineering and crafting of AI apps really steers into sync. But even more fundamentally, as you can kind of see from that kind of linear for agents page, AI apps are fundamentally collaborative, right? You start off with at least two users, the user and the agent. And so if the agent is doing stuff, it's going to be updating state. You need to keep the user in the loop on that. If the user is doing stuff, they're going to be updating state. How do you keep the agent in the loop on that? But of course, it's not just one agent. The whole point of AI agents is that you can spawn lots of them, swarms of them. And if this is how we're going to get stuff done, then we need to be able to collaborate on that. So you don't just have one user in an AI session, you have lots of them. Multiple users, multiple agents collaborating on getting stuff done. And if you look at what that actually looks at for application development, so this here, for example, is a multi-agent, multi-user chat app built on Sync out of Postgres, where the shared state that they collaborate on is in the form of tasks in a to-do list. And so there's an agent on the right that is told to create and monitor a to-do list. And then the agent on the left is told to make a project plan. Then as they're generating it, the user here on the right-hand side navigates to see the to-do list. And then the to-do list, as they're watching it, needs to be live and up to date in the cloud for the agents and in their devices for the users. And so this left-hand agent is then told to distill the plan into tasks and add them to the list. The agent on the right detects the tasks as they come up and starts performing them. And so basically, as you can see, the users and the agents are all collaborating on the same state. And if the agent completes a task, the user needs to be able to see. If the user deletes or pauses a task, the agent needs to know. So you get the point, right? It's not enough to just have collaborative state in the cloud. You also need to have it on the user's device. So you keep the user in the loop. And so with multiple users and multiple agents, if I think about like those sort of approaches to state transfer technologies. There's no way that I would want to build this kind of stuff on like ad hoc imperative data fetch. It just makes far more sense to build it on sync. And so that's why this pattern of syncing data out of Postgres into the client is so important, because it is actually the key way of building this whole next generation of AI apps and agentic systems. And in a way where all this kind of hypey new agent infrastructure all ultimately just collapses down again to good old Postgres. Thank you.
All right, thank you, James. Do we have any questions? Looks like Rustam has a question. There we go.
Hello, can you hear me?
Yes, we can hear you, Rustam.
James, great talk. Thank you so much. My question is about the server Postgres. Do you support the sharded Postgres?
So, could you just describe specifically the sharded architecture?
Not a monolith, not a single cluster. Like, what if I have like multiple sharded Postgres on my server?
I mean, if you're, for instance, having different data in different instances of the Postgres, then you.
Looks like we lost you again, James.
Sorry, something with your mic. I cannot hear you.
Hey, sorry to drop out.
Now it works. Yeah.
Yeah, apologies. So Electric doesn't do anything special at the moment to sort of join that data back up for you. But if you imagine, for instance, syncing out of different shards into different collections in the front end, then you could use that kind of D2TS capability to join back up in the client. Across a number of the other, there's a bunch of these different sync engine technologies, and they would maybe have sort of different support for different topologies. With Electric, I know that like we support syncing out of multiple instances, but we don't do anything special to kind of join it back up for you.
I see. Yes, thank you. And another question. You talk about Tanstack DB, but I heard there is some work on PG Lite. So are you moving away from PG Lite, or like what's the story there?
Yeah, sure. So, PG Lite is another project that Electric develop. Just for context on it, so it is a lightweight WASM build of Postgres. So it's explicitly it's just a build of Postgres. So it just like is the Postgres code base, but it's compiled to be able to run in WASM in the browser using the browser storage mechanisms, and then with some additional stuff like kind of reactive live queries and a sync plugin and so forth. And so, yes, in a way, like PG Lite and Tanstack DB for application development would be alternative technologies that you could use for a kind of client-side store. PG Lite, for application development, it's around a sort of 3 or 4 meg download size. It obviously gives you like full Postgres. It has extension support, so you can get a lot of very advanced stuff if you needed to do things like vector stuff or analytics or advanced queries. So if you kind of need a fully featured database in the client and are happy with the kind of overhead of the bundle size, then that's kind of what it's good for. Tanstack DB is in a way a kind of database without the database. It's just like it has this collection primitive, and then it has this kind of query engine, but it's much, much smaller. So it's literally around 20 kilobytes as a library download. And so for kind of probably most mainstream applications, it's maybe a better choice because it's a much smaller dependency, it's much lighter, it's also much more performant in the way that it runs the live queries. So I would say that probably.
Looks like we've lost you again, James.
Of apps, Tanstack DB maybe where things are. but there's lots of other good use cases for PG Lite. So, for example, people are using it in dev and test environments. It just got built into Prisma, for instance, as the default local database. You can have it like embedded in CI environments. You can have it embedded in like a web container. So sort of PG Lite sort of seems to be being used more for these types of environments where it's sort of useful to have a very lightweight database to maybe sort of run in a reproducible environment, whereas Tanstack DB is more sort of optimized for application development.
I see. Thank you so much.
All right. Do we have any other questions? Anybody? Okay, that was a great presentation. Thank you, James. We will be back on Tuesday, July 8th for compiling Postgres to WASM with PG Lite with Sam Willis.
There we go.
I know, there it is. More explanation, yay. For our August 12th event, we will be celebrating World Elephant Day by presenting the story of the first PG Day with Federico Campoli and a community talk with Stacy Hazler, president of PGUS. Upcoming conferences are FOSSI, July 31st to August 3rd in Portland, Oregon. PGConf NYC will be September 29th through October 1st in New York City. And PGConf EU will be October 21st through October 24th in Riga, Latvia. We will send a link by email when the video is ready, and watch our social media. You can find us on LinkedIn, Mastodon, and Blue Sky by searching for Bay Area Postgres. As always, we are looking for speakers, so if you or someone you know is interested, please contact us through Meetup. Thank you everyone for attending. Thank you again, James, for a great presentation, and we will see you next time. Bye-bye.
Awesome. Thanks very much for having me. Cheers.